Okay, this lecture is on the geometric, the binomial, and the power series, and it's a way to introduce you to the power series. So we start off here with the geometric series. Recall the formula we used when we obtained our partial sums for our geometric series G. We had that 1 plus x squared, etc., up to x to the nth is equal to the fraction with 1 minus x to the n plus first power in the numerator and 1 minus x in the denominator. The left-hand side of this is the n plus first partial sum of the series. N equals 0 to infinity, x to the nth power. The series is convergent for many values of x to the function 1 over 1 minus x. Okay, so we can actually calculate the error in the n plus first partial sum. It is 1 minus x minus the n plus first partial sum is equal to 1 over 1 minus x minus, okay, our formula, right, the 1 minus x to the n plus first over 1 minus x. And when you do the arithmetic on that, that'll be x to the n plus first over 1 minus x. So if you take an x whose absolute value is greater than 0 and take a larger power of n, you'll see that this error can be made as small as we like. And so this series, which is the sum of x to the nth power for n equals 0 to infinity, that is called the geometric series. All right, so our next step is we're going to talk about the binomial series, and we're going to build up to this and do a little review along the way. We're first going to talk about the binomial theorem. The binomial theorem says if you've got numbers a and b, if you take a plus b to the nth power, that will equal k, the sum of k equals 0 to n, of n choose k, a to the kth power times b to the n minus kth power, where n choose k is equal to n factorial over k factorial times n minus k factorial. Okay, so for example, if we have a equals 1 and b equals x, my 1 plus x to the nth power is going to be 1 plus n choose 1 times x plus n choose 2 times x squared plus etc., etc., up to n choose n, but n choose n is equal to 1. And so our function here is expressed as a finite series, as it were. In fact, you can think of it as being an infinite series if you just say all of the coefficients of the powers of x are 0 after the x to the nth power. Yeah. Let's play with this. Okay. First, okay, n choose 1. Okay, this is n factorial over 1 factorial times n minus 1. You do the math on that, it reduces just to n divided by 1. You take n choose 2, you do the math on that, it'll be n over 1 times n minus 1 over 2. And if you go in general, okay, you have a pattern here. Okay, and what is the pattern? That if n chooses k, for n choose k, that's equal to n over 1, n minus 1 over 2, etc., till the bottom is built up to k. Okay, And so you reduce the numerator by 1 every time you build up the denominator by 1. And so it's this extended product with k factors in it. So let's work some examples here to see how this goes. You can it'll actually speed up your work if you have to do a lot of stuff with powers. My 1 plus x to the 4th power is 1 plus 4 over x, 4 over 1 times x. Then we have the second term, 4 over 1 times 3 over 2. See, we're taking the top one down and we're building up the bottom. And so we continue on like that until we get to the x to the 4th power term. And the next term, if we were to continue to do it, we would have the 1 minus 1 is 0, and so we would have a 0 here from now on, okay? But this reduces, and you will recognize that this is 1 plus x to the 4th power. Now, let's play with it a little bit. What if instead of a positive whole number, if we had a negative whole number, 1 plus x to the negative 1st power, if we play this game, okay, we can do our reduction. You see we have things cancel out nicely, and this becomes just 1 minus x plus x squared minus x cubed, and so forth. So this becomes what we could call the alternating geometric series, okay? And so if we go back to the geometric series and replace my x with negative x, okay, then this is just exactly my 1 over 1 plus x power. So it works. This is something which we did this nonsense game with it, okay, and it came out that it would get me the same thing as my geometric series would do. So this is interesting. Now let's do this with n, instead of being an integer of some sort, let's have it be a fraction. Okay, 1 plus x to the 1/2 power, which is, okay, again, how do you even do this? But let's just go through using the game we were playing with the coefficients, this process. So I have 1, okay, my exponent divided by 1 times x. Then I have 1/2, okay, and then reduce that by 1, that's negative 1/2. Then we have on the denominator 1 and 2, building up the denominator. And so we continue in this way, okay, building up. And we say, oh, we get to the 4th power, and let's just stop. We do our calculation here, okay, simplify it, and so we have 1 plus 1/2 minus 1/8 x squared plus 1/16 x cubed, and we think we've got a pattern, but then no, it's negative 5 1/28 over x to the 4th, and then I go plus THD, and then terms of higher degree, and so I have other terms where x is of higher degree over here. Okay. Now, this should give me a way of approximating the square root of 2. Let's see here. Okay, so if I let x equals 1, I go 1 plus 1 to the 1/2 power. I then put in 1 for every x. If I do that, I get an approximation of 1.3856, etc., etc. You see it there. I square that, and it gives me 1.955 and junk, which makes it plausible that this would give us an approximation for the square root of 2 if we ran it out to enough terms. So, that's kind of interesting. Okay, we'll come back to this in a later section. Okay, so for real, the binomial series now. Binomial coefficients. Given a real number alpha, define alpha choose n as alpha over 1 times alpha minus 1 over 2, and keep reducing the numerator by 1, keep increasing the denominator by 2 until the denominator is built up to n. Okay. And then the binomial series is equal to 1 plus x to the alpha power, which is 1 plus alpha choose 1 times x plus alpha choose 2 times x squared times alpha choose 3 times x cubed, and so on forever. Okay, that's the binomial series. And now we come to the one last slide, that what this was all building up to, the binomial series, or the power series. So given coefficients a1, a0, a1, a2, etc. forever, we can calculate that f of 0 exactly, and we can estimate f of x for x not equal to 0 by taking partial sums of the series. For values of x closer to 0, we will have better approximations by this method. When we have good knowledge of the function f for values near x, we can use the form f of x equals a naught plus a1 times x minus a plus a2 times x minus a squared plus a3 times x minus a cubed, and so on forever. This is called a power series for f at a. And we will come back to this, trust me.